to take a look next with you at monosubstituted cycloalkanes. So let's take a look at something relatively simple to start with, and that is toluene. So we'll just put that CH3 right there. Right? Now I'm going to draw this a certain way just to make our Newman projections a little bit easier to look at. So that CH3 group that we have there could be pointing up or it could be pointed down. So I'm going to choose to have this pointing up. So here is our chair conformation, and I'm not putting in all of the other atoms right now, but this would be pointed down, this would be coming up, so that CH3 would be pointing up here. And then what I want to do is I want to look down these bonds. So if we were putting our little eyeballs in, we would want to look down those bonds. Now remember we kind of just said before that, hey, axial positions are less stable than equatorial positions. So as we go through and do this rotation, let's just first take a look at it. So we're going to rotate this around and we're going to end up getting this, this Newman projection down here below. Before we do that though, we're going to do our chair-chair interconversion. Right? So what's going to happen when we do that interconversion is that number 1 is going to get pulled up to this position. Right? So what we're going to have here is an H pointing up and an H going kind of at our equatorial position. Because remember, we said that everything that is axial becomes equatorial, right? So kind of the way that we start off here is we take our number 1 position and we pull it up to that position, right? So that would be our second chair, something that looks kind of like that, right? Our first chair looks like this, right? So that position and that position are moving. They're all moving, really. So that number 1 position comes up here. There's your number 1. That number 2 position becomes right there, right? So you're going to end up with that at the equatorial position. Now, when we look at this and look at this as far as our ball and stick model here, we can really see the structure a little bit more clearly. So again, models help with this. But here's your carbon 1, right? We said that one was an H pointing down. We're coming over. Here's our methyl. That's pointing up. So this is a good drawing, or good depiction of our chair. And what we want to do is we said we wanted to look down this bond here and that bond, right? That's kind of like where your wavy line going to the eyeball is. So we're going to rotate this around and we're going to get this, and then I'll just align it a little bit better. So that's what we're going to draw right now, this. And remember, when you see something like this, the first thing to do is to not panic, right? So what I always tell students is start off with a circle and a dot, right? Circle's behind, dot is in front. So I've given you guys a template here, but if you didn't have one, you'd start off by doing this. If we just look at this gauche one. So here's a circle, a dot, here's another circle, and a dot. Right, so we can say at least that is occurring because we can see that that's these 2 carbons, right? Now off of those carbons, we have a CH2 in the front, right, connected going down, and then in the back carbon, we have a CH2 pointing up. So what we're going to do then is we would come down here and draw a CH2, and then we'd come up here and draw the other CH2. And remember, in this conformation, we want to have a staggered conformation. So that locks us in here to an atom being up and out, right here, and then up and out. And then on the back side, we have to put it in between. So we're going to do this. So if you can just practice drawing that out, then you're pretty much golden as far as drawing a Newman projection of cycloalkanes. Now that CH3 is here, right? And then I'll just use this since I've already drawn it out. So put in H's everywhere else. Now technically, you need to put these H's in because remember, if you don't, the end of a line really represents a CH3. All right, and now when we look at this, that CH3 that's right here is actually gauche to that CH2. All right, so right here we are gauche to each other. All right, so there's this interaction there that's a little bit tighter. Now, what would happen if we looked at our other chair? So here's our other chair-chair interconversion, and we're going to look down these bonds that I highlighted as red. So let's take a look at the JMO, see what that looks like. So as we look at the other structure here, here's our carbon 1, here's our carbon 2, and we want to look down these bonds right now. Right, so we're going to swing this thing around just like so and look at it like this. Right, so that's what we want to draw. So here's what we do now. Draw a circle and a dot, and then another circle and a dot. Now off the dot in the front, you're going to have a CH2 pointing up, and in the back you have a CH2 pointing down. All right, so let's see if we could draw that, and I'll just draw that out for us here. So again, here's your circle, your dot. Those are the two carbons we're looking down. And as we look down there, right, if we look down this bond, that number 1 position, that CH2, that thing's pointing up right now. I'll just write it like that. And in the back, we're pointing down. And again, we're locked in right now. So that means we need to draw these nice little Mercedes symbols here. So we're going to come down and do that. And in the back, because we know that on the chair we are not eclipsed, we are staggered, we're going to put it in just like this. And what we're going to see, right, in that picture, we can see that that CH3 is actually pointing outwards, right? So this is axial, that H pointing down, and that is equatorial. So if we go back to our structure, we're going to put our CH3 right here. Right? That's what we're talking about. So that's that position. And then, as we did so before, H is everywhere else. All right, now when we look at our CH3 relative to that CH2 that we were looking at before, so it's that number 4 CH2, it's the one that's here. That's the troublemaker, right? That is down at this position right now. So that's your number 4. And at that position, we have to keep that one in mind, we are anti to each other. So what that means is that this chair conformation is more stable, right? Because having that at the equatorial position is better. The other thing that we get sometimes is we get these 1,3 diaxial interactions. So we can get these delta G values, and sometimes they're given to you. I'd give them to you on a test, and we can look and see what's the energy that it costs to have one of these substituents at the axial position. So if we look back over here, it's called 1,3 because there's an interaction between the axial positions at number 1 and number 3. So here we're equatorial, so there's no such interaction that needs to be included. But if we go back and we look at that axial form of toluene, right? So here we have position, if we just call that number 1, we have an axial position here, 1, there's a carbon atom, that's 2, and that's 3. So there's another axial position. So that's a 1,3 interaction. And then look, 1, 2, 3, that's an axial interaction too. So to put this up here has a delta G value. It costs energy to do that, right? And we can find that by looking at tables like that. So putting that CH3 at the axial position costs 1.88 kcals per mole. Well, let's look at some more interesting cases. So we're not going to be dealing with just monosubstitute. That's always easy. You just put the substituent at the equatorial position. So let's look at something like trans 1,3-dimethylcyclohexane. So we have our CH3 here and a CH3 down here. And just for numbering this thing, I'm going to call that number 1, 2, and 3. And that way, when I look at my ring, I'm going to call that 1, that'll be 2, and that'll be 3 right here. So what I'm going to do is I take this and rotate it over on its side, right? Imagine if you were looking at that really bad energy conformation, right? So if it was totally flat, you'd have a CH3 here, and then an H down, right? That's 1, 2, and then at 3, you would have an H that's pointing up, and then a CH3 pointing down. And what we're going to do is we're going to take that number 1 position and we're going to pull it up. That's going to put our CH3 in that top position. So if you could kind of see that without going through that, then that's great. If not, little model can help you on that. All right, now, once we have that CH3 locked up in this top position, we know that the other CH3 has to be trans to it, right? So it's interesting. Where do we put it to make it trans? Well, trans means that we have, if you remember, we have a wedge dash relationship, right? They need to be on opposite faces of the ring. So a CH3 up right here, an H here. H is at number 2. And then at number 3, we have an atom that's coming out just like this. Right, so notice that each one of these carbons that we have something that's up here on the top. The CH3 is on the top, and then this H down here is on the bottom, right? This H that's at number 2, right here, if we look over here, that's on top, right? And then that's on bottom. So if we come over here and look at our carbon number 3, if we put our CH3 at this top position right here, that would be cis. So we don't want that. We want that top position to be related to a bottom position here. So that relationship is going to give us trans. All right, so otherwise they'd be on the same face of our ring. All right, and then we go through and we put in H's everywhere else. So pepper all those H's right in there, and then we're done. Now when we do our chair-chair interconversion, remember that we're not, sometimes these are called chair flips, but when I think of flip, I flip a pancake. So an interconversion, to me, is more descriptive. What that means is that number 1 position is going to be right here. So it's really important to recognize that. Now that top position right now is axial. So over here, remember, when we go from our chair interconversions, the axial would become equatorial. So that means that that methyl group is going to live over here. So it's going to be here. That's our equatorial position. And then that's an H. And then where's my number 3? So notice here, I can't call this number 2. I have to number it the same way that I did before. That has to be our number 2 right now. So this is a number 2, right? And then that's our number 3. Number 3 is the one we're concerned with. So here we were equatorial, which means now on this side, we're going to become axial, right? So again, equatorial here, axial down here, top, bottom, that's going to be trans. And then we put our H's in everywhere else. All right, now when we look at this and we try to make a guess on energy, remember we said it was 1.8 kcals per mole to have a methyl group at the axial position. So here we have a methyl axial and we have a methyl equatorial, right? And on this side, we have a methyl axial and we have a methyl equatorial. So they're both the same energy in this case. So these guys are simply the same energy. Now that's not always going to be the case. So let's play around with the one that's down below here. So what about this guy? All right, so same thing. Remember, what we're going to do is we're going to imagine that we're taking this. They're on the same side now. And we're going to number 1, 2, and 3. and arbitrarily. By the way, you could have numbered any carbon here 1 and gone clockwise or counterclockwise. I like to keep one of my substituents at this little point just because I think it's easy to put substituents there. So that is coming out at us right now. So as we rotate this thing over and put it on its side, it's going to be going up like this, right? That's your CH3, and that's your 1, 2, 3, and here we'd have another CH3. So that CH3 is going to be at this position here. Now we want the other CH3 to be on the same face. So 1, 2, 3, that means that CH3 needs to be right there because now they're cis to each other. Right? And then we're going to put H's in everywhere else. And there's a pattern to this: axial, equatorial, and cis and trans. It depends on which carbons you're comparing. So I don't like to memorize things, so I just put them in to figure it out. All right, now remember, when we go through here, let's look at this. Here we have 2, right, CH3s that are axial. So if we wanted to calculate the energy, it'd be 2 times 1.8 kcals per mole. We got that from that table before showing the 1,3 diaxial energies, the delta G's. And now when we do this, that number 1 now is going to get pushed down here. That's your number 1. That's 2, 3, so on and so forth. And remember, here we are axial and axial. So now on this side, we need to put our CH3 group equatorial. And then at that other position, number 3, which is now over here, that needs to be equatorial also. So we put that there, just like that. And then we pepper in all those other H's, guys. One of the things you can do, if you'd like, is you can leave out those H's. Sometimes it's handy to keep them in, especially between the two substituents, just to remember your up-down. Now look over here, look. Here we have 2 CH3s that are equatorial. That's a good thing. That means that this is more stable, right? It's usually pretty easy to figure out. Now, there's going to be some cases where it's not such an easy decision. Now, we typically put bigger groups at the equatorial position, but there gets to be a point, well, what happens if you have one big group that's equatorial, but, a whole bunch of other groups that are axial? So there's a tipping point there, right? And in some of these borderline cases, you actually go through and you just count up your delta G's. And then it turns out that the chair that has the smaller delta G would be the one that predominates at equilibrium. Now, one last little note here is bulky substituents. All right, so again, the most stable conformation puts that T-butyl. So for us, bulky means a T-butyl group. A T-butyl, remember, is a carbon with 3 CH3s. So of course, there's other big groups that are out there. That's just kind of the go-to big one in a lot of organic chemistry classes. All right, guys, let's do this one together then. So that's your number 1. That's your number 4. So there's your 1. Here's your 4. So this CH3, just like we saw before, is going to be pointing up right now. All right, now over here, 1, 2, 3, 4, at this position, we want this tert-butyl group to be on the same face of the ring. So this CH3 is on the top part of our bond, right? If we're looking at an H in a CH3. So here we want our tert-butyl group, in this case, to be over here, because then they're on the same face of the ring, right? And then we go through and put in all our other H's in. Now again, I kind of mentioned this before, but if you wanted to leave those out, it certainly would be understandable. All right, now when we do our chair-chair interconversion, that number 1 position here comes down to this position, and then our number 4 pops up over here. Now as we do that, let's see what happens. Remember, axial here, so that's now going to become equatorial. And then let's look at number 4. Here we have equatorial. Now that's going to be axial, right? And then we put our H's in everywhere else. So in a problem like this, just because we simply said putting big bulky groups, equatorial is generally better. We already know that this is going to be our most stable conformation. But let's look at our delta G's. So here we have a CH3 axial. So that has an energy of 1.8 kcals per mole. Over here, what does it cost to put the tert-butyl group at that axial position? Well, let's see. Here's a tert-butyl group here, 5.4 kcals per mole. So if we look at down here below, this is a delta G of 5.4 kcals per mole. So we can see right off the bat that it's better to have the methyl at the axial position, right? Now, occasionally, we can't get these big bulky groups into equatorial positions. So this is a happens occasionally thing. So you're not going to just go straight to this right off the bat and say, oh, it's got to be this weird situation. So in this situation, when we have these two tert-butyl groups, we end up with one axial and one equatorial in one of our conformations, right? And then in the other conformation, we end up having the same situation arise, right? So as we switch over here, going from our chair conformation number 1, we end up with our tert-butyl group now becoming equatorial, and then our equatorial tert-butyl that was on this side becoming our axial position on that side, right? So then what about this? So the deal here is right now these technically both have the same energy, but it's just so horrible to keep that tert-butyl group at that axial position that this molecule tends to adopt a twist boat. And it does a twist boat in such a way that it puts those T-butyl groups far away from each other, right? So remember that position, that is your flagpole. So it'd be horrible to put them there. Instead, we can point them farther away. So occasionally, this is going to be your most stable conformation. And generally, you're looking for those big bulky groups being at an axial position in both of your chair conformations.